Hey guys, Mr. Gucci here to give you today's notes, which is 1.4, how chemistry works. Let's walk through these real quickly and I'll upload them. Okay, so first of all, as you recall, chemistry is the study of matter, the atoms that make up matter, and how these atoms behave, how they interact, how they form and break their bonds. Now, since everything in the world is made up of matter, doesn't that mean that chemistry is the study of like everything around us? Isn't that a lot? And yes, it is a lot. And yes, chemistry kind of is the study of everything around us. And so clearly, since that is a lot, we try to break chemistry up into a few subsections, a few fields of chemistry that really help focus people's studies. All right. So you don't, if you want to be a chemist, you don't have to be like good at understanding everything, like the chemistry of blood and the chemistry of crude oil and the chemistry of whatever this weird hellish reaction is. All right. You can just focus on being good at certain kinds of chemistry. So here we go. All right. The 5 branches of chemistry. The first branch is biochemistry. Now, like the name implies, biochemistry is the study of those chemical reactions that create and sustain life. If you remember in biology class learning about cellular respiration and photosynthesis and the carbon cycle and the Krebs cycle, all of that is biochemistry. So if that interested you, that might be a field of chemistry you're interested in going into. Medicine, biology, ecology, all of these things involve biochemistry. And biochemistry is probably the biggest field of chemistry in this area because this is a big town for the production of medicine. All right, based in Philadelphia, we have Merck. We have a huge office of J&J, Johnson and Johnson. We also have Teva, which is another drug manufacturer in the area. This is a huge drug town. Now, let me give you an example of some of the work that a biochemist might do. This drug right here is called thalidomide. It was invented in the 40s and 50s, and it is a fascinating drug because what it does is it prevents morning sickness. For those who are not aware, if you are pregnant, one of the side effects of being pregnant, one of the things you have to deal with is morning sickness, which is where you just spontaneously get nauseous and throw up in the morning or sometimes the evening as well. And this drug cures you of that. However, the chemists that came up with the process to produce this drug, thalidomide, were also producing as part of the mixture this drug right here. Now they look identical. And if you count up all the atoms, you'll see that they are exactly the same number and type of atoms and almost connected in exactly the same way. There's just one difference. They're mirror images of each other. The drug on the left is thalidomide. The drug on the right is L-thalidomide, literally left-handed thalidomide. And if you think it doesn't make a difference, all right, if you're right-handed and you have a pair of right-handed scissors, hand those scissors off to someone who's left-handed, and it feels really uncomfortable. It just doesn't fit right. My wife knows this. She's left-handed, so making something the mirror image is enough in chemistry sometimes to have some really negative results. So while this molecule over on the left, thalidomide, cures morning sickness, this molecule on the right, just the mirror image of it, causes horrific birth defects. Now, based on what point in pregnancy a woman takes thalidomide, it could do anything from not affect the child at all to cause them to be born without legs or limbs or arms. Even if it's taken early enough, it might cause the pregnancy to end. It might kill the fetus. This is a tragic incident that led to the handicapping and death of tens of thousands in Europe. Now, we never had this problem in America due to a hero, all right, that none of us hear enough about. Her name is Frances Oldham Kelly, and she was a biochemist. And her job was she worked at the FDA in the 1950s. Her job was to make sure that before a company tried to sell medicines and drugs in the United States, to make sure that they'd been adequately tested as safe. Now, when the people that made thalidomide, a German company, came to her and wanted to get it approved, she refused. She said, "No, you haven't done enough testing here. Yes, it cures morning sickness, but we don't know about any of the side effects as a result of this." And she got a lot of pressure from politicians and big business. All right, pass this drug, get this drug to market. We want to sell this drug, right? Does that sound familiar to a lot of you guys? This pressure to get a drug onto the market before it's been adequately tested? Well, her, insistence not to clear this drug ended up saving tens of thousands of lives because by the time she finally said, "Okay, let's see this research," at last all the research came out that showed the birth defects that were being caused by this drug. So here she is getting the Presidential Medal of Honor, all right, Medal of Freedom, I think, from JFK. She actually lived quite a long time. She only passed away about 5 years ago. Okay, so two other branches of chemistry is organic chemistry. Organic chemistry is studying matter that contains the element carbon, such as fossil fuels, pharmaceuticals, and plastic. Another branch of chemistry is inorganic chemistry, which is the opposite, studying matter that does not have carbon in it at all. And that includes metallurgy, mining, electronics. Now, what's this big deal with carbon? Why do we have two branches based on this idea of whether or not something has carbon in it or not? Well, the reason is because carbon has a chemical property in that it forms more strong bonds than any other atom. It can form up to 4 strong bonds. So if you want to make a large molecule, anything from DNA, polymers, plastics, or proteins, you have to use carbon in it, almost certainly, because that substance right there can form big molecules. Whereas, on the other hand, substances that don't have carbon tend to be very small molecules. And that big molecule, small molecule difference is so big that they've broken it up into two branches of chemistry, all right, which is organic, which is those big molecules with carbon, and inorganic, those small molecules without. So if you're interested in working with plastics or pharmaceuticals, most medicines are large molecules that contain carbon. So there is some overlap here. If you want to make medicine, you have to be a little, do some biochemistry and organic chemistry. That's not impossible. That's what my father does. He is a biochemist that also works with organic chemistry. Okay, so another branch of chemistry is analytical chemistry. All right, analytical chemistry is studying the composition of matter, what it's made of, and what it contains. Okay, so for example, let's say that I got a blood test for COVID-19. I went on down to the Quest Diagnostics and they had me sit down. They took a sample of my blood and they sent it off to a lab. And at this lab, an analytical chemist broke down what was in my blood and attempted to find those substances that were evidence that I'd been infected with COVID-19, either traces of the virus left over in my blood or those things that my body produces to fight the virus called antibodies. And so that was an analytical chemist. An analytical chemist might also be someone who, let's say, a fracking well comes up in your town, it gets drilled nearby, and you suspect that it might be doing harmful things to your water supply. Well, you'd call an analytical chemist. They would take samples of your water, send it off to a lab to figure out if that water contained trace amounts of chemical that are harmful to you. It's also useful in forensics, right? If someone is poisoned, or if someone dies under mysterious circumstances, an analytical chemist will evaluate the body on the crime scene to find trace amounts of evidence, like DNA evidence or evidence of poison or gunpowder residue, that is proof that a murder or something foul took place. That's analytical chemistry. Okay? So physical chemistry is the last chemistry. It is, I think, probably one of the most difficult fields of chemistry, but also one that has the potential to pay the most. All right. Physical chemistry is a field of chemistry that focuses on the actual physics of atoms interacting. Why does this atom combine with this atom? And what happens when they do? What properties result when you put these things together? And they try and understand chemistry at the subatomic physical level so that they can figure out ways to combine atoms together to make new substances that they want with the properties that they want. So, for example, down here we have a picture of a liquid magnet called a ferrofluid, okay? Quite fascinating. It's a mixture of different substances together with different properties that, when you put them together, create a liquid that is actually magnetic. I love it. It's fascinating. So if you're interested in material science research like this, nanotechnology, Tesla probably has a lot of people working who are physical chemists to try and come up with new substances that could be the next generation of batteries and solar panels. So that's what a physical chemist does. All right, I'm going to end this video here, y'all, and then I'll break off to another video next. Just anytime video. You want to just end anytime. Sure thing. Okay.